introduction, I talk about these topics. This is the outline of my talk. I first give a brief overview of new lossless data compression coding scheme. Then, in the first half of this talk, we treat AIFE code, almost instantaneous fixed variable length code. Then, in the second half of this talk, we treat ANS, asymmetric numeral system, and AEDS, asymmetric encoding decoding scheme. Huffman code and arithmetic codes are one of the most well-known lossless data compression codes. The Huffman code is the optimal code in the class of prefix-free code, that is the instantaneous code. And the arithmetic code is asymptotically optimal code that can attain the entropy as the length of a data sequence becomes large. But recently, these new codes have been proposed to beat Huffman code and arithmetic code respectively. The breakthrough of AIFE code is using a small decoding delay and multiple code tree. And the breakthrough of ANS and AEDS is the backward order encoding. These new ideas I will show how these new ideas are implemented in these new codes. Now we treat the AIFE code, almost instantaneous fixed variable length code, which can attain better compression rate than the Huffman code. Huffman proves that the Huffman code is optimal in the class of instantaneous code, that is the prefix-free code. And Macmillan proves that if a code is uniquely decodable, then the code length of the code must satisfy this Kraft inequality. Furthermore, Kraft proves that if a code length satisfies the Kraft inequality, then there exists an instantaneous code that has this code length. Therefore, if an optimal code exists outside of the class of instantaneous code, then from these theorems, there exists an instantaneous code that has the same code length as the optimal code. Therefore, we can conclude that the Huffman code is optimal in the class of uniquely decodable code. However, Macmillan's theorem holds only in the case that we use a single code tree. Therefore, if we use multiple code trees, we can attain better compression rates than the Huffman code. However, if a decoding delay is large, such code is not useful. So we treat the code with a small decoding delay, and such code is called almost instantaneous FB code. The AIFB code that we proposed to 15 use two code tree and 2-bit maximum decoding delay. And the AIFB code we proposed 2017 use M code tree and M-bit maximum decoding delay. Last year, Sugiura and Kamamoto and Moria proposed N-bit delay AIFE code. That code uses N-bit maximum decoding delay with multiple code trees. This is the hierarchy of FE code. AIFE code includes instantaneous code as special case. Therefore, AIFE code includes Huffman code as special case. But the arithmetic code is not included in AIFE code because the decoding delay of arithmetic code is not bounded. Now we explain the AIFV code with 2-code tree and 2-bit decoding delay. This is an example of AIFV code. AIFV code uses T0 and T1 code trees. And the source symbol is assigned an internal node called the master node, in addition to leaf. A master code is an internal node that has grandchild. This master node is connected its grandchild by code symbol 00. And the child node is called the slave node, and any source symbol is not assigned to this slave node. And on the other hand, in T1, there is no path that begins with 00. Now, how the encoding works in AIFV code? As an example, we consider this source symbol, a data sequence. We first use the code tree T0. And the transition rule of code tree is given by this rule. That is, if a source symbol is encoded at a master node, then we move to T1 to encode the next source symbol. And if a source symbol is encoded at the P, then we move to the T0 to encode the next source symbol. So the first symbol C is encoded to 11 in T0, and C is a master node. Since C is a master node, we move to T1, and B is encoded to 10, and since B is D, we move to T0, and D is encoded to 1100, and since D is D, we again use D0 to encode the C, and C is encoded to 11, and this node is a master node. We move to T1, and finally A is encoded to 01. Next, we consider the decoding. We use T0 as initial tree in the same way as encoding. We trace the code 1 sequence as long as possible in the current code tree. In this case, we trace 1110 in T0. There is path 11, but there is no path 11. We trace 111, but there is no path 111. So C is decoded. And this node, since this node is a master node, we move to T1. And we trace the 10 in T1, and B is decoded. And since this node is a leaf, we move to T0. And we trace 1100 in T0. 1100 reach to D, so D is decoded. And this node, this is a leaf. We again use T0 to decode the 1101. There is path 11, but there is no path 1101. So C is decoded. And we move to T1, and finally 01 is decoded to A. In this case, any data sequence is uniquely decoded by AIFV code. However, we decode source symbol C, which is assigned a master node. We need to look ahead more 2 bits to distinguish the C and D. Therefore, this AIFV code has the maximum 2-bit decoding delay. Next, we show AIFV code can attain shorter average code length than the Huffman code. As an example, we consider this source distribution. This distribution has entropy 1.72. And the Huffman code for this source distribution is given by this code tree, and average code length is given by 1.8. On the other hand, AIFB code, in AIFB code, T0, average code length of T0 is given by 1.65, which is shorter than the average length of the Huffman code, because we assign a source symbol to an internal node. However, the average length of T1, which is 2.1, is larger than the average length of Huffman code, because in T1 we cannot use the path that begin with 00. The transition probability from T0 to T1 is given by the sum of the probabilities of source symbol that are assigned to a master node. In this case, this master node has only one node, so this transition probability is given by 0.2. And the transition probability from T1 to T0 is given by the sum of the source probability that are assigned to leaves. In this case, this probability is given by 0.8. From these transition probabilities, we have these stationary probability of T0 and T1. And finally, average code length of AIFB code is given by calculated by this formula, and this becomes 1.74. Hence, the average code length of this code is shorter than the average code length of the Huffman code. This transition rule can be included in this code tree like this. In this tree, broken line and straight line represented code symbol 0 and 1. And this notation means that this node is C is assigned to this node, and C is encoded at this node. We move to T1. By using this notation, we explain the n-bit delay AIFB code, which was proposed last year. And this is an example of 3-bit delay AIFB code for source alphabet ABC. For instance, the data sequence BAC is encoded in the following way. We start the encoding with T0. And first B is encoded to 0, and we move to T2. And second A is encoded to 0, and we move to T3. And the third C is encoded to 100, and so on. Unique decodability requires that for any two data sequence that are not prefixes of each other, the corresponding code word sequences must not a prefix of each other. This condition can be checked by extending the each code tree by connecting this part by other code tree. But we cannot construct the infinity code trees. We need to extend the code tree only n bit. Next, we define the mode. Such constructed code tree for each code tree, we trim the all full subtree. Blue parts are trim full subtree that must be trimmed, and the red part is remaining tree, which is called the mode. In the case of code tree T2, which has 0 and 1, 0, is the mode of T2. In the case of T0, only root remains, so the mode of T0 becomes a null sequence lambda. And we can show that the maximum decoding delay of this node, this code tree, this AI n-bit decoding delay AI code is given by the maximum length of mode. In this case, the most long mode sequence has 3 bits. So this AI code has maximum 3-bit decoding delay. Next, we consider the consider the relation between the maximum decoding delay and optimal binary FB code. In the case of no decoding delay, that is the case of instantaneous code, Huffman proved that the Huffman code is optimal. That means Huffman code attains a minimum average code length. And Huffman code uses a single code tree. In the case that the maximum decoding delay is 1 bit, Hashimoto and Iwata prove that Huffman code is still optimal, even if we can use 2 or more code trees. And in the case of 2-bit decoding delay, Hashimoto and Iwata also prove that the AIFE code with 2 code tree is optimal, even if we can use 3 or more code tree. And in the general n-bit decoding delay, n-bit delay AIFE code can become optimal. However, the number of code tree becomes exponentially large as n becomes large. For a given source distribution, we can construct the optimal AIFE code trees by using the iteration algorithm. In the iteration algorithm, some parameters are used, where M is the number of code trees. And for a given parameter C, we optimize each TJ independently by using integer programming or dynamic programming. And then we update the parameters or the newly obtained T. And by repeating this procedure, we can obtain the optimal AIFE code. However, if the number of code trees or the number of source alphabet is large, this iteration does not work because of the time complexity or space complexity. The research about the AIFE code is surveyed in this paper, which is written in Japanese. Since this paper is published in 2021, this paper does not include the n-bit delay AIFE code proposed last year. However, these many topics are treated in this paper. So this paper is a good survey paper, I think. Now, next we treat the ANS, asymmetric numeral systems, and AEDS, asymmetric encoding decoding scheme. These coding scheme can attain almost the same compression rate as arithmetic codes with less mathematical operations. In the case of arithmetic coding, a data sequence is encoded and decoded from the first symbol to the last symbol. Therefore, the code word P is determined from the most significant bit to the last significant bit. However, when we encode the ST, the the latter part of the code word corresponding to these data sequence cannot be determined. Hence, interval is used in the encoding. On the other hand, in the ANS coding, a data sequence is encoded from the last symbol to the first symbol. But the decoding, data sequence is decoded from the first symbol to the last symbol. Hence, the code word is determined from the lowest significant bit to the most significant bit in encoding. And this means that the ANS coding can be realized by using only one integer variable. Therefore, the encoding of ANS requires less mathematical operations than arithmetic coding. ANS was proposed by Dewey 2009 first. But ANS has already been widely used. For instance, Facebook Z standard compressor, Apple L.FSE compressor, and Google Dropbox, Microsoft, and so on. This is because the ANS is not patented. There are several variants of ANS. ABS is ANS for binary source sequence, and the range variant of ANS is like the range coding of arithmetic coding, and the TANS, table variant of ANS, is most simple ANS. There are only a few information theoretic analyses for the ANS. The first one is the research by Dewey and Yoko. They prove that the TANS is asymptotically optimal. Recently, we analyzed the average code length of each variant in detail, and the result is published in this invitation letter, invited paper written in Japanese. However, the content is translated to English, and this English version is updated to archive. So if you cannot read the Japanese, please refer to this English version. In this talk, we treat the only TAN, and for simplicity, we refer TAN just as ANN. And then we show how the ANS can be generalized to AEDS. In both ANS and AEDS, a data sequence encoded from the last symbol to the first symbol in backward order. And the data sequence is decoded from the first symbol to the last symbol in forward order. Let S script S represents a finite discrete source element, and ST is an IID data sequence, and P is source probability distribution. In the ANS, we use the set of internal states, which is represented by X, and X is consists of integers n plus 1 to 2n minus 1. Therefore, the size of set X is n. X sub S is the subset of X corresponding to source symbol S, such that X's are mutually disjoint for different source symbols. And all union of all X's is equal to n. We represent the size of Xn by ns. Then from this relation, this will have this relation. And we select N and NS that satisfies this relation for every S. Since XS and YS has the same size, so we have one-to-one correspondence between SY and X. And this one-to-one correspondence can be represented by two functions, C and D. And for simplicity, we assume that C and D are given in this law. The encoding of ANS is encoded in the following way. We first select the state Xn, which is from X. X is consists of N to N minus 1. And repeat this mapping from time t equal capital T to 1 in backward order by calculating this mathematical operation. Beta t is the binary code word of source symbol ST, and XT is the bit length of beta t. And finally, we obtain this code word sequence, X0 beta 1 to beta t. In decoding, a code word for a given code word sequence, X0 beta 1 beta 2 beta t, we repeat this mapping from t equal 1 to capital T in word order by calculating this relation. Then we can obtain the original source data sequence. In this talk, we don't explain the relation of this mathematical operation in encoding and decoding. If you want to know this relation, please refer this paper. But the bit length of code word beta k satisfies this relation because the xt xt satisfies this inequality. So bit length of code word satisfies this inequalities. And from this relation, bit length of code word satisfies this relation. Therefore, bit length of code word is close to the ideal code length log 1 over ps. LG log means that the log function with base 2. Now we extend the AEDS from the ANS. AEDS was proposed ourselves this year. We first generalized the set of internal states to an arbitrary finite set, alpha 1 to alpha n. And we also generalized this mapping by two functions, E1 and E2. E1 gives the code word beta t from source symbol ST and internal state XT. And E2 gives the next state at the time t minus 1 from ST and XT. In the same way, this mapping is generalized by two functions, D1 and D2. D1 gives the source symbol from code word beta t and state internal state xt minus 1. And D2 gives the next state xt from code word beta t and state xt minus 1. The set of this code word, this function is called the AEDS. As an example, we consider the case that source symbol and set of internal states are given by these one. Then encoding function E1 and E2, decoding function D1 and D2 can be represented by this trellis diagram. Each node on the right side represents the internal states alpha 1 to alpha 5 at the time t. And each node on the left side represents the internal state alpha 1 to alpha 5 at the time t minus 1. And the line connecting the left side and the right side represents the state transition. In encoding, state move from the right side to left side. On the other hand, in decoding, state move to the left side to the right side. In order to guarantee the unique decodability, the set of variable legs at each node on the left side must satisfy the prefix condition independently. So this set, and this set must satisfy the prefix condition independently. Where lambda is a null sequence with legs 0. As an example, we consider the encoding of this source sequence, data sequence, and assume that we select alpha 1 or x4. Then encoding start from the state alpha 1. The last symbol C is encoded to 1, 0, and we move to alpha 2. And the second last symbol B is encoded to lambda, null sequence, and we move to alpha 3. And A is encoded to 1, 0, and we move to alpha 4. And finally, B is encoded to 0, and we reach to alpha 2. Therefore, the x0 is alpha 0. In decoding, we start from the alpha 2, and 0 is decoded to B, and we move to alpha 2. And 1, 0 is decoded to A, and we move to alpha 3. In the case of alpha 3 has only one line, so B is decoded without code word. And we move to alpha 2. Finally, 1, 0 is decoded to C. The information of x0 can be represented with log n bit, but this log n bit can be ignored in the coding rate if the length of source sequence is sufficiently large. In the encoding and decoding of AEDS, we don't use any mathematical operation. So first the encoding and decoding, like Huffman coding, can be realized. But the AEDS has a lot of freedom, so it is difficult to analyze the performance information theoretically. Therefore, we consider a restricted AEDS or the state divided AEDS. Let X sub S be the set of states that are obtained by coding S from the right side. For instance, this set of two nodes are obtained by coding A from the right side, and these two nodes are obtained by encoding B from the right side, and this C is obtained by encoding C from the right side. In this way, these ones are disjoint to each other. Then we call such AEDS SAEDS. In the previous case, this SAEDS is not a state divided AEDS. The ANS, we can show that the ANS is a special case of SAEDS. But in the case of ANS, the difference in code word length of this set and this set and this set must be within 1 bit. However, in the case of SAEDs, we can use any variable length code satisfying the prefix-free condition at each node independently. So the class of SAEDs is much wider than the class of ANS. And therefore, the optimal SAEDs can attain a compression rate better than what was equal to the ANS. Next, we consider the average code length of SAEDs. Let QX represents the stationary probability of state X. Then, one line contributes to the average code length by calculating the state of stationary probability times the source probability times the bit length like this. And by summing all lines, the average code length can be calculated. Next, we show that we can easily construct the SAEDs that has the same average code length as the Huffman code. Let LHS represents the code length of source symbol S in Huffman code, and the LH max represents the maximum code length in the Huffman code. Then we set the size of set X is equal to LH max, and the size of XS is equal to LH minus LHS. And we use a fixed length code at each node. Then we can show that this SAEDs has the same average length, same code length as the Huffman code. For given source probabilities, this construction of SAEDs is not optimal generally. So the optimal SAEDs can attain a compression rate better than what was equal to the Huffman code. Next, we treat the binary source case. Source alphabet consists of A and B. Let P be the probability of A, and 1 minus P is the probability of P. Then we use this SAEDs, which has one node for source symbol B and any node for source alphabet A. We can show that this SAEDs has average code length given by this formula. Then, in this graph, horizontal axis represents the P. P is the probability of A, and the vertical axis represents the redundancy, which is given by the average code length minus entropy. Then, from this graph, this SAEDs can attain a very small redundancy for every P except this region. So to improve this region, we consider another SAEDs. In this SAEDs, 2 nodes are used for B and 3 nodes are used for A. And this SAEDs attains the redundancy given by green curve. From this graph, we can easily attain the redundancy less than 0.015 for any P by using this construction or this construction. Next, we consider the non-binary case. The first case is the case that N over NS is an integer for every S, so symbol S. Then, average code length can be upper bounded by the entropy plus divergence plus sigma. P is given, P is the source probabilities, and Q is given by, QS is defined by this values. And the sigma is a constant, which is approximately 0.086. Next case is a case such that N over NS may not be integer. In this case, average code X can be bounded by this formula. The host term is less than 1. Compared with the previous case, the host term is added. However, in this case, we can use any integer N and NS or each S. Therefore, this second term can be considerably decreased compared with the previous case. The third case is the case that the N is the power of 2. In this case, we obtain this upper bound. And the third term is less than 1. We can show. We omitted the derivation of the upper bound, but this upper bound is presented in this paper this year. Next, we consider the asymptotic optimality of SAEDS. The optimal probability distribution of each state is given by this Q asterisk I. That is, if QXI equals Q star I can be realized, then we can achieve this average code X. This result was first proved by Dube and Yoko in 2019. But Dube and Yoko treated the case that the Q is equal to P, and N tends to infinity. On the other hand, we proved that this result by general Q. Furthermore, we treat the case of finite N, and if QXI are bounded by these by like this, then average code X is bounded by this upper bound. And we show that this relation can be actually realized by constructing the SAEDS in this way. The right side represents X at the time T, and in this region, to KS minus 1 nodes are mapped to 1 node, and in this region, to KS nodes are mapped to 1 node, and the remaining part is mapped to 1 node. Then we can attain this upper bound. We can construct the SAEDS that satisfies this relation. Therefore, such SAEDS attains this upper bound. Now I give the summary of my talk. I first treat the AI-free code that can attain a better compression rate than the Huffman code by using multiple code trees and allowing a small decoding delay. And ANS and AEDS, which can attain almost the same compression rate as the arithmetic code with less mathematical operations. Especially in the case of AEDS, optimal AEDS can attain better than or at worst equal to the ANS and the Huffman code. And the AEDS can realize the fast encoding and decoding, since AEDS does not use any mathematical operations in encoding and decoding. And we showed some example of AEDS for binary and non-binary sources, and we derived several upper bound of the average code length. That's all. Thank you for your attention.
So any other comments or questions? I have a question about ABS. Actually, I couldn't understand the demonstration of the algorithm, but I think there is a two types of direction for encoding and decoding. So one is the reading of symbols in the encoding and introducing direction of symbols in decoding. And another two directions are the writing direction of code word in encoding and reading direction of code word in decoding. So I think there are four types of direction. I'd like to know the relation of the direction, direction. So can we take arbitrary direction?
You mean that in the encoding we...
Yes, this direction is the reading.
Yes.
Right?
Yeah.
Reading of symbols.
Yeah.
Direction of
in the encoding, we read the source symbol from the last symbol to the first symbol, and we move the state from the right side to the left side.
How about the direction of the writing code word? Writing.
Yes.
Right to yes or left to right?
To satisfy the unique decodability, writing must be the so first symbol C is encoded to 10, and then second B is encoded to lambda and C A is encoded to 10. In this way, the code word must write in this way.
Always same as the same direction. So thank you. I see. Any other questions?
Yes, I have. Thank you very much for your presentation. So you presented two types of new source coding. That's right. Which one has more good performance, better performance?
It is a difficult
comparison way.
ANS has been already used widely. So ANS has a very good performance, and AEDS has a performance better than what was equal to ANS. So these two has a very good performance for a data sequence. On the other hand, Huffman coding for a long data sequence, Huffman coding cannot attain a data compression because the encoding is done symbol by symbol. On the other hand, AN and AEDS encode and decode for data sequence at the same time. TNS is encoded symbol by symbol, but in this way, so data sequence, this is the data sequence, and ANS is encoded symbol by symbol. But ANS used n internal state, and usually n is very large, and this improves the compression rate compared with the Huffman code. Huffman coding, we only use one state. One state means the one coding tree. On the other hand, AIFV code use several code tree. So because of this number of code trees, because we use a number of these code trees, several code trees, we can improve the coding rates than the Huffman code. But usually AIF code, we use 2 or 3 or at most 10, less than 10. So AIF code is usually not efficient as ANS or AEDS, because ANS, AEDS, in the case of ANS, N is usually 100 or 1,000 like that. So the number of states are very different from the ANS and the AIS code.
Any other questions? There's no questions then? Okay, so let's start the